Right, in this video, we are going to look at the properties and reactions that esters do. Okay, so esters are weak hydrogen bond acceptors, but not hydrogen bond donors, just like ketones and aldehydes and ethers. They have a relatively weak dipole moment. It's not quite as strong as it is in aldehydes and ketones. This is because there's some partial opposition of the directions of the vectors, as you can see here in an ester, and that sort of takes away some of the polarity. Okay, esters also have an important resonance interaction going on, like so. Okay, and this kind of offsets the fact that even though oxygen is electron withdrawing, it's actually stabilizing the carbonyl group to some extent by this donation of the electron pair, this resonance structure you see at the bottom right here. Okay, so these are kind of offsetting. The electronegative oxygen is destabilizing the carbonyl, however its lone pair is engaged in resonance and it's stabilizing the carbonyl group. Okay, we see this reduced dipole reflected in boiling point difference. Here we have two compounds that have almost the same molecular weight. The only difference is that one over here on the left is an ester and the one over here on the right is a ketone. And we see that the ketone does have the higher boiling point due to the stronger dipole attractions in that type of carbonyl. Their water solubility is kind of similar, a little bit higher for the ester. This is because of the higher carbon to oxygen ratio, but still it's not quite as dramatic as you probably would have expected, going from a 2-to-1 carbon to oxygen ratio to a 4:1 to 5:1 ratio for the one on the part. Okay, when we look at esters, we kind of divide them into two parts that you see here, and you'll appreciate why we do this division when you see the mechanism for ester formation and hydrolysis in a few slides. But we call the carbonyl group and the R group that goes with it the acid part, and we'll see that this is the part that would come from a carboxylic acid in the most popular synthesis. And this oxygen, sp3 oxygen over here, and the R group that goes with that, we're going to refer to as the alcohol part of the ester. Okay, and that's derived from the alcohol part of the Fischer Esterification reaction we're going to talk a little bit more about later. Okay, this is a smellogram. I'm not going to go through it. It's kind of interesting. There's the website down there by a professor in Australia, but it's kind of an interesting graphic of how you can combine an acid part of an ester with an alcohol part of an ester and produce characteristic smells. Esters, one of their main practical uses is in the perfume industry. They smell nice, and their toxicity properties are basically the same as the alcohol and the acid, so you don't have to do quite as much biological proof that they're not toxic because of the fact that they're metabolically turned into the alcohol and acid very quickly. Okay, let's review some reactions that make esters from the past. These were all in Chem 314. Okay, so we have the Fischer Esterification. We looked at the mechanism in the previous chapter, and here we take a carboxylic acid and an alcohol, sulfuric acid, and we make the ester and generate water. And remember, back in that chapter, we also looked at how this reaction could be reversed. If you have a high amount of water, the reaction will go to the left, and that is called acid-catalyzed ester hydrolysis. Okay, we can make it it's a little milder to make it from an acid chloride or an anhydride. Okay, so we take an alcohol, an acid chloride, and some pyridine here to neutralize the excess HCl that would form as a byproduct, and we make an ester this way. An anhydride isn't quite as reactive, but it will do the same thing to also make the ester derivative like you see here. Okay, a third way that was introduced in the ketone chapter is to do the Baeyer-Villiger oxidation, and here what happens is that we insert an oxygen into the carbon-carbon bond of a ketone, and it goes to the more substituted side, or the side that serves as the better carbocation stabilizer, and this would also make an ester that you see here. So here we have a methyl and an isopropyl, and the isopropyl is expected to migrate to oxygen because it will stabilize the carbocation better. That's a reaction that we looked at mechanistically back in the ketone chapter. Okay, let's look at some new ones. All right, so we talked about this one briefly in the previous chapter. This is the acid-catalyzed ester hydrolysis, but it requires these equilibrium considerations. And because of this, very few people want to hydrolyze an ester this way. The more popular way to do it is the base-induced ester hydrolysis. Notice that I was very careful here to use the word induced versus catalyzed, okay? And we're going to see that it's not catalytic in base. We have to use a whole mole of base to make this reaction happen because of an irreversible acid-base reaction that goes on at the very end of this process. Okay, this is sometimes referred to as saponification because this is the key reaction used in making soap. Okay, it's soap making is just ester hydrolysis. All right, we're going to actually have a chapter later in the class called lipids, and we'll look at that at that point. All right, so the sodium hydroxide is going to react with an ester, and the products that you make are the carboxylate salt and the alcohol. Okay, and if you do a pH adjustment, which is just referred to by the word acidify, we usually go down to a pH of about 4. This gives you the carboxylic acid instead of the carboxylate salt. Okay, so here we're just going to go ahead and do the acidification step. Okay, I'm sorry I forgot to add that in, but so we're going to treat this with sodium hydroxide, then do a pH adjustment, neutralize, or actually we're not neutralizing, we're actually making it fairly acidic. We're going to make the carboxylic acid, shown here, and the alcohol. Okay, we'll look at this in the mechanism, but let's see. Let's look at the mechanism. You'll see why we call it the alcohol and the acid part there as well. Here's the mechanism. Hydroxide ion attacks the carbonyl group to make the tetrahedral intermediate. We kick out the alkoxide. Recognize that we could have kicked out the hydroxide, but that would just take us to where we started, so the reaction doesn't move in a forward direction unless we kick out the alkoxide. This gives us the carboxylic acid and the alcohol. Because this is a very strong acid, that proton right there has a pK of 4.7, and this is a strong base. This is the conjugate base of an alcohols, which have pKs of 16 to 19. This last step is not reversible, and it's because of this last step that we don't call it the base catalyzed reaction. Okay, so it's not catalytic because we can't stop this last acid-base reaction right here. All right, let's imagine that we have an oxygen 18 labeled system. So we're going to put an oxygen 18 label here, and sometimes people do the oxygen 18 label by just coloring in the O. Okay? All right, so we're going to make this. It's where the 18 is here. All right. Okay, and you see that the label is going to totally end up in the alcohol part. If we label the other carbonyl oxygen, it might stay, it might not, but there's a reverse this first process, since it's reversible. If we don't have the whole system O18 labeled, we might lose the O18 label if it was there. Okay, so this is another reason why we refer to this part here as the acid part. And this as the alcohol part. You can sort of see how this labeling study supports that division of the ester, right? Okay, we can add organolithium and Grignard reagents to esters just like we could with ketones and aldehydes. However, another process takes over. All right, so what's different here is that we're going to add 2 moles of our Grignard. Okay. What we're going to end up with is a tertiary alcohol, unless R1 is hydrogen. Okay. And what we end up with is a tertiary alcohol that has 2 identical groups on the alcohol-bearing carbon. Okay, and we're going to just treat it with mild H3O plus to turn the alkoxide into the alcohol. All right, we're just going to take a little bit of creative license here and pretend that our Grignard is a carbanion, so we can sort of look at what's happening a little better. Okay, so, right, remember that the dipole goes that way in a Grignard reagent. All right, so here's what's happening. We're adding it to get the tetrahedral intermediate. Tetrahedral intermediate is collapsing. This gives us a ketone. You may think, hey, that reaction that's not finished yet here, this looks like a pretty good reaction. Could we just stop it here? Well, you really can't. What the problem is that as far as the reactivity goes, in general, ketone is more reactive than an ester. Okay, so even if you're very careful to add exactly 1 mole, as the reaction progresses, the ketone here and the ester that you started with would have to coexist, and each new molecule of Grignard reagent that you add would have a decision whether to react with the original ester or the ketone that you just produced, and the ketone would eventually win out. Okay, as its concentration gets higher, it becomes more of the reaction component, and eventually the only way you can get a clean reaction is just to add an excess of the Grignard reagent. So what happens then is you take the ketone, do the reaction you saw in chapters I guess 13, 14, and 17, add that Grignard to the ketone to get the alkoxide, and then you protonate it to produce the tertiary alcohol. All right, so how do you know to use this reaction instead of the addition to a ketone or aldehyde? The giveaway is the fact that you have 2 identical R groups attached to the alcohol carbon, like you see there. Okay, and that's the sort of cue that you should be using this reaction to prepare something. Okay, hydride reduction for an ester occurs much like it does for a carboxylic acid. Okay, so we're going to react this with lithium aluminum hydride, and we're going to find that we add two hydrogens here. Okay, so you get the primary alcohol, and you get as a byproduct the alkoxide of the alcohol part. Okay, so when you protonate it with do the aqueous workup, you get two different alcohols. Oftentimes when we have like simple esters like methyl esters and ethyl esters, we don't care about the smaller component, but if the R2 component is somewhat large group, you would actually want to account for it. Okay. All right, so lithium aluminum hydride. Again, we're going to take the creative license that lithium aluminum hydride is synthetically equivalent to H minus. Okay, so we're going to add hydride to the carbonyl group. We're going to get our tetrahedral intermediate. Tetrahedral intermediate collapses to produce an aldehyde, and an aldehyde we are well know is reactive to lithium aluminum hydride, so it just reacts to additional moles of lithium aluminum hydride, and you eventually end up with these two alcohol products right here. Okay, if you had used lithium aluminum deuteride in this reaction, you would end up with two deuteriums right there. All right, the book makes a little bit of mention of this. I'm not going to in this class, but there are sort of fancy designed aluminum hydride reagents that will allow you to stop the reaction at the aldehyde stage. I think it's sodium tri-T-butoxy aluminum hydride. Okay. And I know people that have tried this reaction, but it requires kind of a high skill level to do it. A lot of people just don't weigh things out properly. These reagents are kind of decomposed in the air, so it's hard to weigh them to the accuracy that you need to. Okay, and one final thing here. Sodium borohydride is not reactive enough. There are a few like slightly more reactive esters that will react with sodium borohydride, but for the most part, sodium borohydride just isn't reactive enough to reduce an ester. It's lithium aluminum hydride that you need. Okay, here's a few other reactions. If we very carefully exclude water and take an alkoxide, you can get a transesterification reaction. This is a completely equilibrium process. The only way you can really make this go to the right is to take a really cheap alcohol like methanol or ethanol, and you operate under really anhydrous conditions, and you'll pretty much overwhelm whatever R2 you started with, and you can make the equilibrium go completely to the right that way. So for example, if we take this species here, okay, and treat it with sodium methoxide and ethanol, it's will have such a large excess of ethanol molecules that we can count on this reaction essentially going to the right and producing the ethyl ester plus the isobutyl alcohol. The reaction's still in equilibrium technically, but because we have ethanol as a solvent, this reverse arrow tends to be very small. Okay? All right, we can react esters with amines. Okay, and this is our amine has to have at least one hydrogen at nitrogen, so only ammonia. Primary amines and secondary amines will do this reaction. If you heat the system, you'll generate the amide plus the alcohol that comes from there. Okay? All right, and the reason this reaction goes to completion is because of the stronger resonance interaction that you have in an amide. Okay, so this is a stronger resonance. This is a lot more stabilizing to the carbonyl system than you have in the ester, and for that reason, this reaction goes completely to the right. There's also a reduction of basicity. We'll talk about this in the amine chapter, but an amine is basic, but an amide is not basic. Okay, so there's a kind of a neutralization that's occurring in this reaction as well. So we're just going to look at the mechanism for the reaction at the bottom. Okay, so we're going to take this ester here. And note here that there's this carbon between the alkoxide and the OMe group, so the ester is on the left side here. Okay. All right, so we're just going to add the nitrogen is going to serve as a nucleophile. We're going to make our tetrahedral intermediate. Okay, this is going to fall apart like so and give us this. For some reason, this extra hydrogen didn't come through here. Sorry about that, but what's going to happen here is that a self-neutralization is going to occur, and this is going to go this way. You can write a more complicated mechanism. This isn't any more or less correct. We swap out the proton first. Okay, let's see, we're going to now get the protonated ester. Okay, or protonated amide rather. And we're just going to lose the extra proton. So this is an alternative process that really gets you to the same place. Okay, let's look at a few practical applications here. Let's predict the product of this reaction. The first one, we're going to show two products, and this is an optically active ester. It's the S enantiomer. And the important thing to note is that this is the CO bond that we cleave. We don't do anything to that CO bond, right? So we're going to treat this with KOH, and then we're going to acidify it. And we're going to make that alcohol with its retention of configuration. It's still going to be S. And we're going to make the carboxylic acid. Okay. All right, and the next one, we're going to treat this ester with a large excess of allyl Grignard. And what we're going to do is we're going to add 2 moles of allyl group here. We're going to make a tertiary alcohol, and this is our product. Okay, so there's our Grignard right there. Okay, and we've added the allyl groups. We've also, as a result of this, made a molecule of methanol, but again, that's kind of probably not the real reason anybody would have done that reaction. All right, so this is a type of ester known as a lactone, which is a cyclic ester. And its reactivity is basically the same as a normal ester. It's a little bit more reactive, but we're not going to worry about that here. We're going to treat this with excess ethyl Grignard and H3O+. What we're going to do is we're going to add 2 ethyl groups here. And because the alcohol is attached, or the alcohol part here is attached 2 ways to the carbonyl group. Okay, it's attached directly by the CO bond, but indirectly by these 4 CH2 groups. What we're going to find here is that the alcohol in the product is still attached to what was originally the carbonyl group. Okay, so we're going to label the carbonyl group that way. And this is the product that we're going to have right here. Okay, the reaction went by cleaving. You follow the mechanism from a few slides ago. That's the bond that we would have cleaved, and we would have done nothing to the 4 CH2 groups that connect that oxygen to the C double bond O the other way. All right, the next last one here is a double labeling experiment. Okay, so we have oxygen 18 in the alcohol part of the ester, and we're treating it with lithium aluminum deuteride. As you recall, in the other explanation, we put 2 deuteriums where the original carbonyl group was. Okay, and this is the 2 products that we should expect. We should expect the oxygen here in the deuterium part to be just normal isotopically normal or natural abundance isotopes of oxygen in that one, and we should expect the bottom one to be O18 labeled. Basically what's happening here, you should not see any product that has both the deuterium and the O18 in it. Okay, because the O18 was in the alcohol part, it stays with the alcohol. Because the deuteriums, or the lithium aluminum deuteride, affects the acid part, the deuteriums go with the acid part of the molecule. All right, so let's write a mechanism for this reaction and then explain why the equilibrium goes to the right. There's really 2 good reasons. Okay, without knowing anything about mechanisms or anything, you can probably think of one of the reasons here is that we have relief of angle strain, right? The 5-membered ring is not nearly as strained as a 4-membered ring. Okay, so that's one driving force for this reaction. All right, the mechanism. I've sort of drawn it in such a way that I'm pointing you toward the answer. Okay, so we're just going to attack the carbonyl group that way. Let's see, I'm giving you the self-neutralization mechanism here. That's what we call this process. Okay, we're doing it this way. We're opening the 4-membered ring, and this is going to remove that extra proton in another self-neutralization process, and that's going to give us the product. Okay, reason number 1 is that it's relieving angle strain. Reason number 2 is that in amides we have a much stronger resonance interaction with the adjacent lone pair. So that's probably the more important reason right there. Even if this ring, this lactone ring was not strained, this reaction would still proceed to the right. Okay, I think this is the last of the esters. Okay, that's just the answers there. And finally, there's a third reason as well. It's relieving the basicity in the system. Again, this is an issue we're going to talk about in amine chapter, but amines are basic, amides are not. Okay. And, oh yeah, one other thing. Transesterification has lately become a really important reaction. This is in the production of biodiesel. Okay, so here is your typical fat molecule, a triacylglyceride. Okay. And if you do a transesterification, sodium methoxide and anhydrous methanol, you'll get a long chain fatty acid that's a methyl ester. And what you see is something that's comparable in its elemental composition to diesel fuel. It's not quite as good as diesel because these oxygens don't do anything for you in the combustion process, but this is a very hydrocarbon-rich molecule, this methyl ester down here, and it can burn quite effectively as a substitute for diesel fuel. Okay. All right, and so that's where we're going to stop this one. The next one is on amides. Okay.